Hi everyone, so here we're introducing you to a new section of chemistry called nuclear chemistry. So in nuclear chemistry, we're dealing with just the nucleus, so the protons and the neutrons inside of that nucleus. We're going to need your notes as well as table N and table O. So we're going to talk about radioactive isotopes, or just do a quick review of them. I'll talk about something called natural transmutations, different particles that you'll see, a decay series, and questions. So this will be a little bit longer of a lesson, I apologize. So to remind you, radioactive isotopes are when the proton to neutron ratio is not a 1-to-1 ratio. So you might have more or less neutrons than you normally would. Than you would the number of protons. Remember, the protons have a positive charge, they're constantly repelling one another, so the neutrons are in there to kind of balance out those charges. And these isotopes will naturally decay, and we're going to talk about how they naturally decay here. So they do so by natural transmutations. So if you think back in bio, a mutation is a change in DNA. DNA is located in the nucleus of a cell. So here in chemistry, transmutations are going to be changes inside of the nucleus of an atom. So we're talking about changing the number of protons and the number of neutrons. These happen naturally, so you'll actually see that these isotopes spontaneously decay or they emit another particle. And what we mean by spontaneous is that they don't need energy to do this. They'll just do this naturally. They will change the element's identity if the number of protons change. And generally you see this as one reactant, and I'll show you guys these in just a bit. Here are the particles that are on table O. So we have a whole bunch of different particles here. You're used to the ones closer down to the bottom, the neutrons and the protons. But here we're introducing alpha, beta, gamma, and then positron particles as well. The notation is going to be the isotopic notation. The numbers at the top represent the number of protons and neutrons, or your mass number. The number at the bottom left is the atomic number, or the number of protons. If you want to figure out the number of neutrons, just subtract the top minus the bottom. We also have symbols here too, and I'll show you how to draw some of those. So the first particle we'll talk about are going to be gamma particles. So if you think back to like Spider-Man, he gets his superpowers by being exposed to certain types of radiation. A lot of times they're talking about gamma radiation. The notation for this is going to be a 0, 0, and then the gamma symbol kind of looks like a little Y. And the symbol for this is going to be, it looks like an upside down ribbon that you would use. So again, just to draw that a little bit more nicely. So that's your symbol. It'll have 0 protons, 0 neutrons. These are very strong particles, so they actually need to be stopped by several inches of lead. So if you go to the doctor's office and you need x-rays, and they put like this vest on you, that's actually to help prevent certain types of particles for your x-ray particles. And your gamma particles are actually very similar to x-rays in energy. This does not change the atom itself because you have not changed the number of protons. And again, they are similar to x-rays. X-rays and microwaves. But these are more or higher in energy than X-rays or microwaves, so they have high energy. Alright. Okay, so the next particle we'll talk about are alpha particles. Here we have the symbol, let me go back. And again, the notation is going to be located on table O for you. We have 4,2-He, or 4,2 and the alpha symbol. And the symbol is going to be, again, that alpha symbol, kind of like the fish that you see. So if you notice the notation, it's 4,2-He. He is helium, so this is actually the nucleus of a helium atom. Not the whole atom, it's just the nucleus of it. So it has a mass number of 4 and an atomic number of 2. So it has 2 protons and 2 neutrons. So again, 2 protons, 2 neutrons. I got this because the bottom number is the number of protons, and you subtract 4 minus 2, that gives you the number of neutrons. It can be stopped by paper or human skin. It's not really very powerful. Let's see, so human skin or paper. So if something's going to emit an alpha particle, it will change the atom itself because you are going to get rid of a certain number of protons. Some other things here, again, let's just write out, it's the same as the helium nuclei, not the helium atom, again, the helium nuclei. It carries away 2 protons, or, yeah, we'll say carries 2 protons from the nucleus. And a gamma particle will also be released. And notice I'm using the symbol now. So gamma particle is released. So let's go through some of the, or what this really means. So here on the bottom left we have 23892 uranium. It's a very heavy, unstable nuclei. And it's actually going to emit an alpha particle, so that uranium is going to emit an alpha particle and then become 23490Th. So it's going to actually release an alpha particle and change the nucleus itself. So let's show you how this happens in a notation. So if I have, or in an equation, if I have 23892 uranium, it's going to release an alpha particle. So actually, let's look at table N to show you. Let's find 238, and it's actually all the way down at the bottom. We notice the decay mode is an alpha particle, so we know we can release an alpha particle. So we'll release 42He, and then this is what a problem might give you. That's it. Or even might just give you the 23892 uranium, and then you have to figure out it's going to release an alpha particle and what else it's going to release. So with these are my favorite type of problems. You'll love these because they're super simple. They look complicated, but they're not. So let's take a look at the numbers at the top. Well, first of all, we want to figure out what this next element will be, because if you notice, we have 238 at the top. That arrow can be an equal sign, and you have 4 plus an unknown number. So you know that 238 is not equal to 4. But here you just kind of solve for that unknown number. You kind of figure out what that the mass number is going to be. So if we look at this, we'll end up having 234 as our unknown. Let's do the same thing at the bottom. We have 92. That arrow really means an equal sign, and 2 plus an unknown number. I'll do this as another x. So 92 is equal to 2 plus x, excuse me. So when you solve for x, you just should see that it's 90. We can then look at our periodic table to figure out what element is number 9, or which element has the atomic number of 90, and it ends up being Th. So again, sometimes you might see this equation. Let me box in what I would want as a response, like all of that. That's your answer. Everything else is just work for me to show you how to do these. So again, uranium's super heavy. It's going to emit an alpha particle, and then that element's going to change into a different element. This is not a chemical change, it's a nuclear change that's happening here. So let's go through. Francium-220 is also going to emit an alpha particle, polonium-239, radium-226, radon-222, etc. So all of these guys will release alpha particles. So you need to use table N to help you figure out what's going to release alpha particles. Next, let's talk about beta particles. So beta particles have the notation of 0, oopsies, let's go with that, 0, negative 1, E. Its symbol can be the beta minus, sometimes you might see the E, but we'll just stick to beta minus, and the number of protons. So let's look at the symbol itself. If we look at the top, or excuse me, the bottom of the notation, it's negative 1. So it's a little weird. It doesn't really have any protons that it's giving off. And then kind of the same thing with the neutrons. But we'll actually show you what ends up happening here. So what's really weird about this is that a neutron actually ends up becoming an electron and a proton inside of the nucleus. So again, weird. Neutron. You can emit a proton and an electron. You can kind of help yourself remember that because neutrons are neutral, right? So if you have an electron and a proton together, that will be a neutral charge. This is unique only to beta particles. I don't want you doing this later on in other parts of chemistry, okay? So a beta particle is essentially a neutron that's released an electron and a proton. So in fact, let's go ahead and write that. So the neutron, neutron releases an electron and a proton. Alright, so what ends up happening? We now know we have one less neutron, so one less neutron in that atom. And we actually end up having one more proton. And it can actually be stopped by aluminum foil. And since you did change the number of protons, you did change the atom itself. Alright, so some other things, let's see, it can also release a gamma particle, so gamma radiation, and again, you end up having one less neutron, one more proton. So let's look at table N. Let's find some examples of things that can release a beta particle, or beta particles. So any of these right there, so it's B or beta minus, so notice that 37Ca, or calcium-37, is beta plus. We'll talk about that later. So all of these will release a beta particle. Alright, all of those, and that's it. Okay, so let's write out a notation for this. Let's use the top one as an example, 198 AU. That's all you're given. Alright, so then you have to figure out what the rest of the equation would be. So we have to look at our reference tables to figure out what the number of protons is for AU. So go ahead and look at your periodic table. So if you find AU, that should be gold, and the bottom should be 79. Alright, so there's 79 protons in gold. So we'll continue on the rest of the reaction. We know we have a beta particle, so it's 0, -1, beta, and now we have to figure out what it becomes, or what element it becomes. Alright, so we have 198 at the top. That arrow is an equal sign. Now, is equal to 0 plus an unknown. So I'm just transferring those numbers at the top just up a little bit more so I can do some work. So since 198 is equal to 0 plus x is equal to 198. Let's do the same at the bottom. And this is where people kind of get a little stuck. So 79 is equal to -1 plus x. Go ahead and solve for x. So again, to solve for x, you need to add 1 to both sides. So you actually should have had 80 here. Double check your math and make sure that you do end up having that. So now we have to figure out what element this is going to be. So if we look at a periodic table, element number 80 is actually going to be mercury, Hg. So again, this is what I would want as a final answer. The other stuff, so that and that would be work. Alright, so let's talk about the fourth particle for today. These are going to be positrons. So your positron particles are 0, oops, I did that again, 0, +1, beta plus, or 0, +1 E. Right? So the symbol would be a beta positive. And let's kind of talk about some of what ends up happening here. In this case, a beta particle, if you see over here, is actually a proton that releases a neutron and an electron. But it's an electropositive electron. You know, electrons are negative. Again, this is the only time I want you to write electrons are ever positive, that I want you to see that. So protons release a neutron and an electropositive electron. And so for the number of protons, so you actually end up decreasing the number of protons by 1. So I'm just to do a little arrow to show decrease by 1. You end up increasing the number of neutrons by 1. And so this can be stopped by just air. It's not anything that's very harmful to us. It's exposed to us all the time right now, actually. And let's think about if it changes the atom. So if you change the number of protons, yes, you will end up changing this atom. Alright, so again, it can be stopped by thin air, and it's a proton that releases a neutron and an electron. So let's go back to table N and find anything that decays via a positron. So we want beta plus, and that's what I'm looking at in decay mode right here. Any of those things will end up releasing a beta particle, or excuse me, a positron particle. Whew. Let's take the first one that's listed right there, 37 Ca. Let's go ahead and write out the rest of the reaction for this. So you have to figure out the number of protons for Ca, so look at your reference table, or your periodic table. Find Ca, which is calcium, and it has 20 protons. So you're going to do the next step. You know that this is going to be a positron decay, right there, because that's what it says. So it's 0 plus 1, I use the beta, plus an unknown. So let's take a look at the top. 37 is equal to 0 plus, oopsies, that should be a plus sign, an unknown. So the top number should be 37. Let's take a look at the bottom. 20 is equal to 1, excuse me, let's write that a little better. 1 plus your unknown. So if you're going to solve for x, it should be 19 on the bottom. So your original element, calcium, has decreased by 1 proton, so now you have the element potassium. Alright, and this is the decay series. I know this is a lot for you guys today, but don't worry, you'll be experts at this. So the decay series is pretty much showing you what ends up forming different elements. So uranium. Uranium is really a radioisotope. It's really heavy, especially uranium-238, and it's going to break down into something a lot smaller. So at the bottom we have the atomic number, and on the y-axis we have the mass number, so the number of protons and neutrons. So here's uranium-238 starting at the upper right-hand corner, and whenever you see any of these decay modes, so they're the crazy arrows, start at the upper right-hand corner. That is uranium-238. So it will release a particle to become, let's see, TH-230 or 234TH. Another particle will make it uranium-234. Then down here you have TH-230. Then, let's see, Ra-226. Keep going, Rn-222. So you kind of keep decaying this, right? So you have to figure out by the end how many, or what it's being decayed by. So pretty much what happens to the number of protons, what happens to the number of neutrons. And I agree these are really, really crazy looking, but don't worry, we'll figure these out. Alright? So let's go through some questions. What nuclear reaction is classified as an alpha decay? So the key word here is alpha. We want to make sure we look for the alpha symbol. So or in the notation. So the notation is 42He or 42 and the alpha symbol. So you want to make sure it's releasing, meaning it's going to, the alpha particle is going to be in the products. So let's take a look at A. Let's see, we have a beta particle in the products, but no alpha. Same thing here, a beta in there. We have an alpha here, that's good. And then let's take a look at D. Well, it does have a helium, but it's not 4,2 helium. We want to make sure it's 4,2 helium. So C is our correct answer here. A gamma ray is best describing as having A, no electrical charge and no mass. Okay. B, a negative charge and no mass. So we know that the gamma ray is going to be 0, 0, gamma. There's no protons, no neutrons. Alright, so the mass is going to be 0, and the number of protons or charge is going to be 0 as well. So we can pretty much eliminate all of these except for A. Which equation represents alpha decay? So here, this time, they didn't give you the actual alpha particle. They gave you X. Don't try to find X on the periodic table. It doesn't exist. That's just your unknown. So you have to go through each one of these equations and try to make sure that this X, or the unknown, would end up being a 4,2He. So let's solve for the top. So let's start with A. So we have 116 equal to 116 plus an unknown. So automatically the mass number should be 0. And I'm just going to get rid of that to show you. So we know it wouldn't be an alpha particle. Let me just kind of keep going here just to remind you. 49 is equal to 50 plus your unknown. Subtract 50 from both sides. So your unknown down here is negative 1. Well, that's a beta particle. So that's not going to be the correct answer. And keep going through each of these. And I'll pause here, but I want you to pause actually. And I want you to keep going through all the answers. So at the end, you should find that D is your correct answer. We have 222 equal to 218 plus your unknown. Oops. So the top number should be your 4. The bottom number, 86, is equal to 84 plus an unknown. So that should be 2. So that's 42He. Alright, which types of these radiation has the greatest penetrating power? Meaning, what do you need the most protection for? And think back, this is just a memorization. You should have C, gamma. The diagram shown represents radiation passing through an electrical field. The arrow marked 2 would most likely represent. Alright, so here this is a little crazier. you pretty much have a lead block, so this box essentially, and it's emitting certain particles. So here, particle 1 is really attracted to the positive charge. So if something's attracted to a positive charge, that's going to be negative. Take a look at 3. This is attracted to a negative field, so this should be positive. The only thing that goes straight through that's not affected by the positive or the negative charges should have a neutral charge. So we want to show, the diagram shown represents radiation passing an electrical field, the arrow marked 2. Alright, so 2 should be something that's neutral and has no charge to it, so we should have C, gamma radiation. Which radioisotope is a beta emitter? Now, for how will you know which one each one of these are? There's no way to memorize it, so of course, go ahead and check Table N. And I want you to go ahead and check Table N right now. Go ahead and pause me. Alright, so using Table N, you should see that 90 strontium is a beta emitter. 220 francium is alpha. 37K or potassium, we wasn't there, and then we have another alpha particle, so A is your correct answer. Just to give you guys a heads up, some of these questions are older questions that I've had from the previous version of the reference table, so like the reference table changed in 2011. So you'll have the newer, you'll use the new reference table, but some of the questions might refer to particles that used to be on the old reference table, so don't worry about that. And if you do see that none of the right answers show up, let me know. Alright, summarize. Use Table O and Table N to help you figure out the number or the particles and the beta or the types of emitters, if it's an alpha, beta, or positron. Alpha and beta also emit gamma radiation, which can be quite harmful to us. And the natural transmutations, those are pretty much reactions that have one element or one reactant, and then that decays down spontaneously into other products. Have a great day, guys.